Thanks. Yeah, so my name's Reid Wightman. My background is I'm kind of an industrial control system. I like to call myself a reverse engineer of industrial systems, mostly looking for vulnerabilities in ICS equipment, ICS protocols, ICS software.
Yeah, I'm Jimmy. I have a malware analysis background, primarily software reverse engineering. Started working at Dragos and started doing embedded things, so here we are.
Yeah, this talk is kind of interesting just because my background is like a vulnerability hunter. I'm always finding bugs in industrial control stuff, and this is actually a piece of malware that's taking advantage of some of the types of things I would used to find, for my day job. I guess this talk really involves maybe the most different reverse engineering topics because we're looking at a piece of malware that actually does some things to an embedded system's firmware. So in order to achieve the analysis, we had to do, malware reverse engineering, hardware reverse engineering, looking at the firmware to figure out exactly what the payloads were doing, looking at the protocol to see how the network protocol worked. We even had to do a little bit of lock picking, and we had to buy a lot of stuff from Canada, it turns out. These industrial controllers can be a little bit hard to get a hold of, and a big portion of the stuff that we bought actually came from Canada. So let's dive in.
Oh, yeah, thanks. So I guess before we get started, let's just a little bit of background so you understand why we were looking at this stuff. TRISIS was a event. It targeted a gas facility in Saudi Arabia. And what happened was it resulted in a system shutdown. So this piece of malware affects a safety controller, a safety system, and their job is to guard certain industrial processes. So the simplest example is if you think about a pipe during gas refinery, it can only be a certain temperature, and if it gets too hot, it will just blow up. And so the safety system's job is to make sure it never gets to that pressure and cut everything off and maybe do some backup steps to maybe release the gas or whatever. And so they infected the system, something went wrong, and it caused a shutdown at the plant. In particular, the safety system that the victim had was a Schneider Electric Triconex system. So how did this attack work? Well, there was a sys-connected workstation. Some will hear us call it an engineering workstation. The attackers moved a malicious Python executable to the workstation. It's like py-to-exe. And that exe handles connectivity with the Triconex, and that's how they uploaded the payload. So, little diagram, right? So they established access on the sys-connecting system. The exe transfers PowerPC payloads to the actual sys. The PowerPC payload runs, exploits the controller, loads a rootkit, and then the next step over here would have been to leverage that access for disruption of the industrial process. So this is what we think the intended goal was of this attack. What actually happened, though, was after they uploaded the program, something went wrong. And we're not really sure exactly what that is. We're going to talk about some of that stuff later on. Some of the reporting said that the rootkit broke in this step, and that may be the case, and we'll kind of go into what that means later. So the reason this attack is very important for the industrial control systems community is this is the first sort of deliberate, first basically piece of malware that could have legit caused physical damage since Stuxnet. If you're really looking at things, though, this is kind of the first attack on civilian infrastructure that could have caused, that had the potential for injury, which is why in our community it's a pretty big deal. So what is TRISIS? It's malware that infects and installs a rootkit on the safety controller. It's a PC application. There's a trilog.exe. Trilog is actually the name of a regular application that does some logging and monitoring of the Triconex. They created a py-to-exe binary and just named it Trilog and loaded it. There's a separate library.zip component that actually implements the custom TriStation protocol. It's a proprietary protocol that you use to communicate with the Triconex. Besides that piece, there is the PowerPC payloads. There's a embedded payload inside of the Python script. It's called preset status field. We'll talk about what that does in a minute. And there's the inject.bin, whose job is to run the exploit and install the imain.bin rootkit. Imain.bin is an implementation of a network command inside of the Triconex operating system. There's also the fourth unknown payload. Once the rootkit was installed, you would have had to do something else to bypass the controller to cause it to not react to a unsafe situation. We don't have that payload. We don't even know if it actually uploaded the controller. There's conflicting information on exactly what happened in that part of things.
Yep. So one of the questions I got asked out in Hallway Con right before the start of the talk is, what is a SIS? So it means Safety Instrumented System. A SIS controller is really a programmable logic controller. If you're not familiar with PLCs, what they are little embedded computers. They have input and output cards, right? So they run this special code on them called ladder logic programs. An engineer will write this ladder logic, and the logic basically says, go read these inputs. They might be analog inputs or digital inputs. The inputs come from sensors out in the field, at your cookie plant or whatever you happen to be running, and perform some operations on that input. Treat this variable as a temperature, and if the temperature is getting too high, maybe control this output, which would turn off the heat. That sort of thing. So a logic program, though, is really compiled code. When an engineer is writing up this form of ladder logic, for a lot of both safety systems and regular PLCs, what you're actually doing is compiling byte code. So you're taking the reading of these inputs and the writing of the outputs, turning it into executable code, and then you're loading it into the controller, a lot of times without authentication, unfortunately. So basically, PLCs can be thought of as systems that run untrusted code from whoever knows how to load it into them. A safety controller, of course, is usually designed to safely shut down a process. When it sees stuff going out of whack, it will have logic in it that will put the process into a safe state. So really, it's meant to protect people from getting injured. But a safety controller isn't the only thing. Like a lot of people have been saying, oh, if you own a safety controller, that means you can automatically win and you can automatically hurt people and cause explosions and that sort of thing. And that's not true at all. A real engineer isn't going to trust all of this automated computer stuff, and they're often going to install mechanical fail-safes. So they might have some pressure relief valves that are mechanically activated. Like when pressure gets too high, it's literally a spring that lets this disk push up and release pressure. They might also have pressure burst disks to do the same sort of thing. So there are a lot of other safety controls that are put in a normal process control system, but at least owning the safety instrumented system is kind of a first step that an attacker needs to achieve if they want to cause that kind of mechanical harm. So the Triconex safety controller most safety controllers have a lot of redundancy built in, and the Triconex is, as its name implies, it's triple redundant. It actually has 3 processor modules, all of which each scan cycle, they will read all of the inputs, decide on what the outputs should be, and there's a voting algorithm. Basically, if 2 out of 3 of the processors don't agree on what the state of the process should be, you're going to go into shutdown because the output cards will see that there's disagreement and there's no way to reconcile that disagreement, so we should fail safe. The Triconex has a lot of other redundant stuff, but for an attacker's point of view, it's really just a PLC because there's one network interface, and that one network interface and one network protocol loads the data into all 3 processors and communicates with all 3 processors. That's all kind of hidden from you as the user. The redundancy is really meant for dealing with equipment failures. It has nothing to do with defending against an attacker. So this is a picture of the Triconex, the small part of the Triconex. We'll see the full system in a minute. The Triconex has a couple of different modes of operation that are controlled via this key switch. These modes of operation, I think the important thing to take away from this is normally when this thing is running, you would put the key into this run mode. And this run mode is a special mode that prevents the operator from loading new logic into the controller and also prevents any operators from actually writing to the controller. Think of run as being some sort of read-only mode where you can connect up to the controller via the network, read status data out of it, but you can't actually try to assert any outputs manually, and you can't change the logic that's currently loaded into the controller.
All right, so one of the things we wanted to do with this talk was not just tell you kind of the what of what happened. We just wanted to walk you through how we went through analyzing it because there were a lot of different steps involved. So the very first thing we got was a collection of software, one of which was the PyDaxi thing, which we unpacked, uncompiled, and then began to read. So the first thing up here, you'll see this import TS high. That was the piece inside of that library.zip file. The library.zip implements the tri-station protocol. We're not going to go into those details. You just read the Python code and it tells you how it works. Like, it's not really an interesting reverse engineering task. The thing we were really interested in was this. They defined a function called preset status field with which is a bunch of PowerPC bytes, and then they uploaded it. In particular, it takes this input, and it's kind of cut off on the slide here, but it actually inserts it into this program. That's the first thing it actually uploads during execution. So, whoop, what happened? What did it just do? Oh, there we go. Whoop. All right, so this is sort of the main function. It opens up inject, imain.bin, concatenates them together with some flags, adds some length values, and then uploads that to the controller after the preset status field. So it runs preset status field, puts this value somewhere on the controller. If it's successful, it'll set this boolean to true, and then it actually uploads the payload, the inject.bin plus imain.bin payload. So the first thing we were interested in was, what was this program? How does this operate? So we just dumped the code out of Python here, and then we loaded into IDA as PowerPC and took a look. We wanted to shout out to PowerPC instructions if you're actually here. Your Twitter account kept us sane. A lot of times he tweets basically fake PowerPC instructions. You should definitely go check him out. So we're going to switch over to IDA for a second, and let's see if I can. Oh, well, that's weird. Why can't I see it? 1 second. Where'd my mouse go? Having problems. There we go. All right, so this is, whoops. Oh, wait, I'm sorry. That's my bad. I did that the wrong way. We made some changes. I don't want to show you I'm going to show you the PowerPC for the next step. We just did a hand decompile of the preset status field function because it's just easier to look at this way. So the main thing is it was kind of an egg hunt program. It starts at 800,000 here and then iterates looking for 2 particular values, which may be some kind of version check, and then it sets that value, that 8001, that was passed into that function. So when that PowerPC program runs, it ends up setting the input value to some address on the firmware. At this point, we don't actually know what any of this addressing means. So once we saw that, you kind of make a note of the addresses, and then you move on to the next step, which was inject.bin. And what we'll see is there's also just a lot of unknown addresses going on, and I wanted to give you a sense of the sort of structure of inject so you could see what we were looking at when we first got these payloads. So when you load this into IDA, you get a branch to a function, which is this sub 678. You go in there, and what you'll notice is you sort of have this step functionality. So at the very beginning, you'll see it references address in that 800,000 range, and it pulls a value and then stores it into a register, R31. And then it starts doing some comparisons. So it moves it over, starts comparing things. It looks for F, and then it bails. Then it looks to see if it's 1. Then later on, you'll see it looks to see if it's 2. And if we zoom out a little bit, you'll notice it's kind of this step logic structure. Depending on what that value is, it'll execute a particular step in the program. When we go examine one of the steps, say like this function here, what you'll notice is there's a lot of these subs that just return hard-coded addresses. And part of that, I think, is an optimization in PowerPC because you can't load a 32-bit address in a register because they're 32 bits wide. You can only load 16 bits, and you got to load the other 16 bits. We have a lot of those going on in here. And so sort of our first target was figuring out what the addressing was. Like, what do we have to, what are these things? Why is it setting these values, et cetera? So go to the next step. So in order to do that, we actually had to get hardware, right? So.
Yeah, so we couldn't find a place to download the firmware for these safety systems, right? It's not something that you can just like go on Schneider's website and say, yeah, I want to get a firmware update. If you're a customer of theirs, you have to have a support contract, and it's pretty expensive. And even then, you usually have to pay for a firmware upgrade or something. So we were like, well, the easiest way to get the firmware is probably going to be buying equipment and pulling the firmware out of the equipment. So we go to eBay, your source for safety controller and industrial surplus. So we spent about $5,000 building this safety controller. That includes a really heavy backplane, a couple of processor modules, power supplies, and an Ethernet card. And this is just fun because some of the components actually came from here. So what we finally built was this big rack. And this thing, like I said, I think in total this weighs maybe 80 pounds. That's a banana for scale. So ours has 3 of these processor modules. Each of these is a processor module here, and this one doesn't have its casing on it, so we could hook up logic analyzers and stuff to it, watch things happen. This is a network card, and this is a digital output module. We don't really need to talk that much about the details, but each of the processor modules actually has inside of it 2 CPUs. We might cover that at some point. But when you pull apart the actual processor module, there's a board inside which has these 2 processors. It has really obvious BDM headers. If you're familiar with embedded PowerPC, they have a 10-pin header similar to JTAG for debugging. We have a JTAG tool, but it wouldn't work with this particular CPU model, just due to probably software, or it could be some fun hardware stuff that we can talk about. But each of those processor boards also has just 3 2-megabyte flash chips. So we extracted the firmware the old-fashioned way, which is desoldering flash memories from the circuit board. It's pretty fun, except that these are industrial components, so they are conformally coated, and that stuff's nasty. This was kind of like a gelatinous silicon conformal coating. Basically means you have to really carefully scrape all the conformal coating off the board so that you can hit it with heat and not get all this smoke and nasty stuff in the air. But we desoldered the flash memory chips, read them out with this memory reader. I bought this a long time ago. It's made by a little company out in Vancouver. More Canadian products, fun. And then we get the firmware out. So then we start having to analyze the firmware. And of course, this is like a low-level embedded system. The firmware, has basically a handwritten board support pack that sets up some of the CPU registers to, talk to external chips and all that stuff. We kind of want to get through that normal bootloader stuff and just find where is the main part of the firmware here. The bootloader, though, kind of looks through a table on the firmware, and that table has a bunch of entries in it for parts of the flash that it either decompresses or copies to RAM, depending on some boot parameters that we don't fully understand. But that's okay. We were able to eventually figure out how that decompression worked. They used an LZW compression algorithm, but they had some weird thing with bit endianness that took us a little while. It turned out running the code in QEMU was really helpful. So thanks, Ramiro. I know he's here. We owe him some beer. Yeah, hey, thank you. Thank you for helping us getting this to run under IDA plus QEMU. That was really helpful because then we could write some Python to extract the components of the firmware, which was really nice. So the firmware has a bunch of different segments to it, and at first it didn't make a whole lot of sense what was going on, except we started to realize that there's 2 processors in this system. One of the firmwares is actually meant to be run by the other processor. The first processor boots up, decompresses the firmware, loads it into some shared memory, then toggles the reset line on the second processor saying, hey, you're ready, you can wake up and start executing your code now. But there were a couple of other main firmwares that were kind of meant for debugging, firmware updates, that kind of thing. So we want to focus, though, on the main firmware. So we get that loaded up into IDA. We figure out where it was located on that flash chip and start running.
Right, so there were actually a lot of steps to get to that point, right? So even loading up the firmware initially was difficult to look at because we don't know what the memory map is. When you look at the MPC 860 specification, it's a great read, it defines a memory map with special registers. And those registers are offset from another register called the IMMR. However, if you load up the firmware in IDA and you tell IDA that it's using an MPC 860 and then you check all the boxes for I/O, memory map, layout, whatever, it assumes that the IMMR starts at 0, and it puts those registers starting at 100. Well, actually, they start at 0 all the way down. So the problem with this, though, is that the interrupts are actually mapped to OX100, and in this firmware, the IMMR base is set to 022000000. And so we actually need to create a segment and then offset it so we could see where those special purpose registers were, and then also get the interrupts in the right location so that we actually had interrupts in the firmware so we could actually start looking at the code, define the network dispatcher, define the different parts of the firmware. So we loaded it into IDA with the PowerPC processor, still the same one. You tell IDA, don't do any of that I/O and memory map interrupt labeling stuff, and then we just label the IDB with IDA Python. And that looks a little gross. Basically, I just scraped the PDF files with the documentation, did some Emacs wizardry, turned them into dictionaries, loaded that in IDA-Python, and then wrote some scripts for labeling the memory map, labeling the interrupts. And as a result, we get a sane IDB. I included comments and things, so I knew exactly what things were. With a new segment, all the special purpose registers labeled, and then at every offset for the interrupt, we actually have code, and then we have all the entry points into the program. It's not just sys reset. Sys reset is what happens when the thing turns on. There's also the in-service call and a bunch of other ones that we had to look at.
Right. So we want to focus on that main firmware, right? Because we want to know TRISIS is reading and writing some RAM addresses, presumably, that are mapped or used by that main firmware, and we want to know what the heck the addresses actually mean. So we get this Triconex firmware operating system loaded up, and I use operating system in air quotes because it's tiny. It only has 27 system calls. For reference, I think the Linux kernel has like, 330 system calls. If you're familiar with embedded stuff, ThreadX, I think, has like 70 or 80 system calls that are provided by the kernel. So this thing is tiny. But we at least know like where the system call handler is now. We also know where all the interrupt handlers are for handling external interrupts and all that stuff. So back to that question, right? What are those offsets? And they're the 80006C and 19AC68 and the other addresses that we were looking at in inject.bin. So we want to start, we have the main firmware, which is loaded at offset 0. We have to start making some memory segments for the data that we don't know what it is. I mean, we just basically go in and make these memory segments in IDA so that we can start getting cross-references, and we can say, oh, I see this data address that the exploit is using is also used by this function in the operating system, so now we can start mapping what those addresses actually mean. So this was the end result, what we had in IDA as all the memory segments that we mapped based on the Triconex firmware, where it was touching things in memory. And some of these might be shared memory with that other processor. Some of these might be external chips. We don't know what all of them are, but we at least know like where the RAM segments are and some of that. So I guess you want to talk about?
Yeah, so we go back to inject, so that I didn't have to like scroll through all the PowerPC code. We sort of provide this nice hand decompile. It's not completely simplified, but the summary of this is, one, it sets some stack variables at offset 60 plus 12 to 9002 and 0. It sets a couple global addresses, FFD 232, FFB 104. 104 actually gets set to the stack variable, and then the exploit, I guess in the beginning really, it sets up a structure on the stack, and then it sets certain members of that structure to some of these values. In particular, the PI1, which would be the second pointer, it sets it to a 19AC68. It sets the integer member to 1, and then it calls system call 19, or OX13. So the first thing we did was actually just go look at this address, because it's kind of a random address that it submits as input, and this looks like it's just going to be input into the exploit, so this seemed to be the most important thing when we were first starting out. Just did some cross-referencing. What we noticed, it was only referenced in 2 places. It was loaded and stored by the system call handler. The system call handler saves SRR1, so this move from SRR1 instruction just moves the value of SRR1 into the destination register there, and then we take that value and stored it at 19AC68. The system call handler then is just saving SR1 to that address. So we went to go look what SR1 was, and we took a look at the system call documentation, and it turns out the SR1 register gets bits from a register called the MSR. You keep going and look for the MSR register, and it turns out the MSR register stores a bunch of status information for the running program, things like power management, whether or not interrupts are enabled, data address translation, those kinds of things. And in particular, there's a privilege level that it stores. If it's 0, you can execute user and supervisor level instructions, and if it's 1, you can execute just user level instructions. And they only include that in this nice little footnote that we actually copied out. It was the very bottom of a table. They didn't really advertise it. Anyway, so to summarize what the system call does, the service call handler saves the MSR of the program into SR1. The syscall handler checks if the system call is from user mode. If it's in user mode, it turns on data and instruction translation. It issues a sync so that all the processor boards are kind of executing with the same view of memory. It saves all the user mode registers at that offset, and in particular, it stores SR1 at 19AC68. On return from the system call, the OS loads the registers from the same save location. It issues an RFI that then copies that value from SR1 to the MSR register. So if you modify, the sort of TLDR here is if you modify the SR1 save location, that will end up becoming the privilege level for the running program when you return. So after looking at sort of how the system call handler worked in the addressing, we started to get a sense of what was going on. So we went and actually examined the system call that they were exploiting. So if you look at the system call, what you'll notice is it actually takes the same input structure that inject built, which kind of makes sense. And in particular, I don't want to go into too many details here, but I left it for later on if y'all look at the slides. It looks like it's just fetching some structure from an array, and it fetches some values, and then kind of does some arithmetic on it and writes to an address. The important point here, though, is that 19AC68 gets set here. So when it does this dereference here in this calculation, it's actually going to cause a write to that address. The rest of the input is more for bypassing a bounds check here and some other things, and we'll walk through that in a second, like right now, right? So if we actually evaluate what happened, here's our inputs. Next slide. The very top of the code, right, it calculates an index value, it subtracts 1 from that. It actually passed in 1, so that becomes 0. It dereferences R12 here. Since index is 0, that basically goes away. That becomes V60. Then it uses the index value here, and the 1, the integer 1 that it's set here, does a comparison, it skips the bounds check, comes down here. Then it sets R9 and R10 to these offsets, which it actually set in code to 900, 9002, and 0. It does a comparison, 9002 is not less than 0, so it skips this block. This doesn't matter because the exploit doesn't use it. And then it does this subtraction, which is just 9002 minus 0. So sort of TLDR, the whole exploit, they sort of turn the exploit into a function that just does an arbitrary 2-byte overwrite to whatever address you specify. So that's kind of the end result, is it dereferences the SR1 save location, stores 9002 in it. So since we know what that thing is, we need to go just look at the bit mask and figure out what's going on. And it turns out if you kind of, just look at it in binary, the 17th bit is a supervisor bit. It sets that to 0, and that ends up becoming the privilege escalation on return. So this is the actual whole control flow, because I didn't walk you through everything that the malware was doing. The trilog.exe, that preset status field value, the input it takes is actually a control value that has a step and like a debug symbol and a timer in it, all in 16 bits, or 32 bits, I think, total. The inject waits that amount of time, and that's a step 1 in the exploit, or in the inject.bin payload. Then it uses the exploit to confirm the MSR state of the running program. So it actually checks to see if it's actually in user mode. If it doesn't see the expected MSR state, it'll bail. Then it uses the exploit to see if it can read a value from its own stack and write it back. So then it tests that it actually has access via the system call handler. Then it uses the full exploit for the privilege escalation, which is what we just talked about. And the rest is just sort of basic installer stuff that you'd see anywhere else. It copies imain.bin to the executable firmware region. It patches a consistency check so that the firmware OS ignores the result of a consistency check. So the firmware actually reads RAM in the firmware and compares it to make sure that everything's straight. After that, it overwrites the jump table in the network command dispatcher with the address of imain.bin. That's actually pretty important. The network command dispatcher, the way it works in TriStation, in the TriStation protocol, you can send a command, and you send a number. All the commands are just numbered like an enum. And that number ends up becoming an index into a switch table that just jumps to the block to execute that function. The TRISIS attackers found an empty jump table location, 29, that jumps to the default case in the switch statement, and it writes imain's address there. So what that means is you just send a regular network command using regular TriStation protocol with the value 29, and then you can execute the code for your rootkit. The network command allows arbitrary read-write execute of memory, bypassing the key switch. So once it's installed, if you switch that key switch back to run mode, you can still execute code in the controller, which is sort of the intention in terms of capability here. The ability to modify the controller despite what the engineers have set that key to. The reason this is allowed is that the key switch is only enforced in software, so all the network commands check what the key switch is before executing. So the developers have just decided which classes of commands are not allowed and which are. It's not like some kind of hardware thing that sets memory to read only or anything like that. It's just completely enforced in software. The network command is actually straightforward. It fetches the packet, the TriStation packet, and then it gets a sub-command value. Where is that? Command here. It gets a sub-command value that it switches, and there's a value for read, that causes it to read an arbitrary address. There's a value for write that causes it to write whatever data you gave it. Interesting thing here is it checks to see if it's in the executable firmware region. If it is, it flushes the cache and disables the interrupts. And then execute just basically creates a function pointer of the address you gave it and executes. And then it sends a reply back to the attacker with a command code of 150 to let it know everything went okay. This is actually kind of important, this little part of the end, because the original reporting on this event said that TRISIS hooked a network function, which it didn't really do that. This network function didn't exist beforehand. They installed their own one. And one of the clues here was it just branches back to the regular command dispatcher return. Normally when you think about function hooking, I'm sure a lot of you here know that, right? Like you write like a jump to the beginning of the function, you jump to your code, and then you jump back, right? If you're not filtering or doing any input, or you don't need, or you don't feel like executing, you just jump back to the regular function. This doesn't jump back to any other code or any other network command like that. So why did they pick 29? Well, it turns out I ran some IDA Python and things to parse switch statements and just do some basic set stuff. And it turns out they actually had 12 options for a network command. There are 12 network commands that have empty jump table locations. There are actually 15 different hook options in memory because it turns out the dispatcher is actually 2 tiers. There's a primary dispatcher that does sort of a binary search over network command codes to figure out which ones to execute, and then at a certain point it dumps off to a switch statement, and then some of those tables can dump to a secondary dispatcher that then executes a switch statement. So the end result of that is you actually have 12 different network commands that you could use to hook, and you have 15 different addresses that you would actually write to implement that. So what that means is if I wanted to install the TRISIS rootkit, and I could use a command code besides 29. There are a bunch of different, there's like 28, 27 that you could have used to do this. The reason we're bringing this up, a couple things. One, they actually have a name for that network command. So inside of the Python, there's this tscnames.py that's basically just a bunch of enumerations of tri-station status codes to their names. And the ones in the beginning, I think between 0 and OX81, are function commands. And 29 has a name, getMP status. But that function doesn't exist in the firmware. And so what we think is maybe the attackers had a software engineering workstation version software for maybe a different version of the firmware. Maybe they had a document that enumerated that number, or maybe they just made it up. But this isn't actually something that Schneider actually developed inside of the firmware. And the funny thing is they did that, and at first I thought, well, maybe they made it up to make it look like it was a normal command. But when you actually look at the Python, they just have a function called execute exploit that passes 29, so they didn't really hide themselves too well. They give it away right away. So the end result of this is there are actually 14 like easy-to-make variants of TRISIS with only a 4-byte modification. You have to change 2 bytes, 2 bytes where the write is, and then there's a check where you have to change 2 bytes to the new address, and you can install it somewhere else.
Yeah, so we heard that the victim, of TRISIS had a couple of plant shutdowns over the years, and they were trying to diagnose exactly what happened. This happened a few times where their safety system actually failed and tripped their plant offline, and they stopped production. So we were really curious, does this thing work? So of course now we have a working Triconex controller, so of course we're going to run it. But of course, our Triconex controller that we bought was secondhand. The reseller, industrial surpluser that we bought it from, wasn't kind enough to include a key, so we had to go and do some lockpicking. So this was just to set that key switch mode between remote, run, and program. In fact, when we had this thing delivered to us, it was in remote mode, so we had to flip it over to program in order to actually load the TRISIS payloads into the controller. When we run TRISIS, the actual trilog.exe executable, we get a lot of output from the application. It doesn't seem like it was meant to be accidentally run by an operator, because it prints out some kind of funny statements that would probably alarm a real engineer, saying that it's writing a new program to the controller and erasing a program and doing all this status checking. Not the sort of thing you would normally see from a professional piece of engineering software, but this is just showing where it's actually loading that fstat, that initial write to that variable, the 80001 or 8001. 0.001 value to that memory address, and it's getting decremented each run of the code. And then the trilog.exe is just pulling the controller, waiting for that timer to count down to 0. Eventually, the timer counts down to 0. The trilog.exe checks and verifies that the rootkit has been installed, deletes the inject.bin portion of the code from the program table. It actually doesn't delete it, but it actually overwrites it with a blank program. It's actually a little bit of a pain to like add a program and then delete it using the tri-station protocol. It will definitely, your engineer, when they reconnect the next time, they will be prompted by the software saying some major code changes have happened on the controller. You know, you should, you need to download all of your code again, that sort of thing. But once this, all this is done running, the only way that we can actually remove TRISIS, or the TRISIS rootkit, from the system is to reboot it, essentially. If you don't want to power off the whole system, you need to individually remove each of the processor module cards so that they are depowered and their RAM is cleared. So TRISIS is really only resident in RAM. It never actually writes out to flash memory, so it's possible to clear it out via that reboot. That actually, I think, makes the forensics of it a little bit trickier, because the plant tripped supposedly offline a few times. Of course, if you're going to take the safety controller and send it back to the factory for forensics, there's nothing to forensicate, because if you unplugged it, you lost all of your RAM data, and what's left is just your base program that you loaded into it yourself, the base firmware that was loaded into it by the vendor, and nothing else. So we wrote a little bit of TRISIS post-exploitation code just using that new network command that was injected, just to play around and see, you know, if we could actually get our controller to accidentally trip offline. This is just an example of writing, you know, AAAA to that fstat. That's that same value that's used by TRISIS as its countdown variable. And sure enough, we can actually, you know, write that data to that address, and everything works fine. And you know, our Triconex has been running for quite a while with TRISIS installed. So the long story short is we don't know what actually caused the TRISIS to actually trip the safety controller at the industrial facility. We do, or at least we have heard, that the victim ran the version 10.3 firmware of the Triconex controller. The one that we pieced together off of eBay, all 3 processor modules run version 10.4. We broke one of our processor modules during testing. So I bought 2 that ran the 10.4 firmware, and 1 ran the 9.9 firmware. So I decided, well, I guess I'll try and upgrade the version 9.9 one by, you know, removing the flash chips, reprogramming them, soldering them back down. But there are a few other chips on the board that probably have some memory in them that maybe, you know, the boot is getting stuck. If I had a working debugger, it would be a lot easier to diagnose, but I don't, so it's not. But we ran it against a version 10.4 Triconex with two working processor modules. We also had an anonymous source give us access to a Triconex with 3 processor modules running the 10.2 firmware. It worked there too, no problems so far. You know, we've been running some post-exploitation code to dump and write memory. So it's possible that there's a version, or there's something different in the version 10.3 firmware, either an offset that's being, you know, overwritten that really messes something up, like maybe the network command dispatcher has a different, you know, different address. There's also a RAM-ROM comparison check that gets hooked as part of the TRISIS code. So normally the Triconex system will actually compare what's on the memory flash chip to what's running in RAM, and will bail if it sees something that's wrong, and it actually patches over the branch if equal condition. I think that's right? Mm-hmm. Yeah. So I mean, it's possible the address of that changed in version 10.3, but I'm kind of doubtful, because if 10.2 worked and 10.4 works, why would the offsets of some functions change in the 10.3 firmware? Our best guess is that the attackers had some, you know, third stage payload, something that they were going to do post-exploitation that they either messed up, or the Triconex was in a configuration they weren't expecting that causes it to fail safe. So we did a couple of other things that were fun, kind of post-exploitation. So this tri-station protocol is proprietary. The vendor doesn't actually document it anywhere. So of course we, you know, used a combination of the TRISIS malware, as well as, you know, looking at DLLs and things to figure, and looking at packet captures to figure out exactly how the protocol works. We wrote a tri-station, or a Wireshark dissector for the protocol, and, you know, we are able to do file carving. So whenever the TriStation software, which is this engineering software used to load programs into the controller, whenever it actually sends a new program to the controller, we can carve out that file. We get the PowerPC binary. Now we can load up those programs, the actual engineering programs, into IDA and see what interesting stuff we can do. So this is an example of an engineering program that actually writes to a digital output. So this would be something that your safety controller would look at the status of some of the inputs and decide, hey, I need to open a valve. So it writes to an output that would be connected to a valve, and the disassembly ends up writing to this address. This is what one of the digital outputs was on our particular hardware configuration. I wanted to know, I've loaded TRISIS onto my controller. Can I now flip it back into run mode, which is supposedly the read-only mode, and write to that address directly and have it affect a digital output? So wrote a little bit of Python again to use the TRISIS library, and sure enough, we get basically what this does is reads in all of the outputs. It's using the read RAM function to read out that address. Reads in the data, basically, does an exclusive OR with FFFFFF, negating all of those bits, and then writes the data back out to the output address. And sure enough, we get the output 1 and output 2 values that are on our safety controller flip, even though the safety controller is in a state where it should not allow remote operations. That's just kind of like a fun thing, and probably what the attackers would be after. They would want to run this code, put the rootkit into the controller, and then be able to, while the plant is actually operational and running, manipulate some of these output points, and cause some chaos. So what does TRISIS mean for reverse engineers? Well, to me, or at least what I've seen is there's been no other safety system exploit. There's certainly been no safety system or control system rootkit like this that overrides basic functionality of a logic controller. I doubt it's going to be the last. We've heard some telemetry that this activity group that is responsible for writing TRISIS has been on other operator networks looking at different equipment, not just Triconex equipment, but other manufacturers of safety systems. So probably this activity group is going to start developing capabilities, or they've already started developing capabilities to attack other vendor safety controllers. So we definitely need more engineers and even more reverse engineers, kind of looking at not only what's possible with safety controllers, how challenging is it going to be to fix those problems, but also identifying exploitation of those systems. A lot of them use proprietary protocols like the Triconex. These protocols generally don't even have authentication, right? So it's like you can download or send, executable payloads to the safety controller. The safety controller will just run them with whatever privileges it runs code with. On some systems, it actually runs, with supervisor privileges from the get-go, which is unfortunate. But we should start looking more at these proprietary protocols and saying can we at least identify exploitation using the protocol and that sort of thing. So for the ICS manufacturers, one of the things I've kind of been harping on the last few years is that these industrial controllers really have no way for you to tell if the firmware that they're running is untampered with, let alone the logic that your engineer expects to be in the controller is untampered with. So we need some sort of high assurance attestation protocol. And that could be something even like a dedicated serial port with its own processor, right, that has read access to all the memory in the system, that has, some high assurance firmware that's very minimal, that would just let you plug in and say, give me a dump of everything that you're running right now in a way where the main processor can't tamper with it. Which is kind of the next problem, which is that a lot of these systems run their protocol parsing on the same processor that's running this logic, the actual control logic. To me, that's like a big, design pattern that's terrible for security anyway. So in this case, we have this, in the Triconex system, we have this same CPU, literally the same CPU on the board running both network commands and executing logic. This could have been a lot worse. Obviously this rootkit could have eventually, and it may eventually find a way to write firmware. When you do raw flash writes, you have to read in and do this erase block stuff, where you have to read in a block of data, erase the block of data, write out the new block of data that you want to have written. So writing flash memory tends to be a little bit more tricky, but it's not something that would be terribly hard for an attacker to figure out how to do. And I mean, finally, I guess, the trilog.exe didn't have to do any authentication to the controller, right? It just said, here's the executable payloads, like go run them, and they get run. So those are kind of the big technical takeaways.
Oh yeah. So we want to talk about what tools we use, just to highlight some other maybe stumbling blocks that may have happened. We used IDA Pro for the majority of the analysis, the sort of static RE. We noticed that it had some problems cross-referencing certain strings. So we found a function that we identified as a serial printf function on the controller, and it would load a string, and like IDA knew it was an address, and then we go to the address and we noticed that like there's no cross-reference getting generated. And so I wrote some IDA Python that was cross-referencing. I was like, why is this happening? Well, later on I realized if you go into the processor options, there's this thing called aggressively convert add lis to offsets, which will take constants, and if it thinks it's an address, it'll make it an offset. So then you kind of had the opposite problem. So whereas before you have to look at a constant and figure out whether or not it's an address, in this situation, you look at addresses and hope they're not constants. So you kind of have to pick which way you want the needle to flip. With QEMU, we sort of talked about this already. In order for us to debug this stuff on QEMU, we had to use you had to select this other virtual machine. I think Reid can talk more about those problems.
Yeah, I think the default QEMU system PPC machine is like a PowerPC G3 or something, which like loads some firmware at some address and won't let you load like a code snippet at an address of your choosing. It's a little bit silly, but with the Vertex ML507, it basically loads with like no memory loaded at all.
We also, I tried to use RetDec. We didn't have the PowerPC decompiler from IDA, and we were kind of on a timeline, so we were trying to look for some ways to make things a little bit easier. RetDec was sometimes helpful. First, it takes a while when you load a firmware image, even a small one, to decompile everything. There's some options where you can tell it to decompile certain functions. But when you actually look at the whole firmware, for example, a service call, which is pretty important for the inject, looking at a service call 13, it gets translated as return X. Like it doesn't identify that a system call is happening. And so it kind of gets masked inside of the decompilation, which is a bit of a pain looking at a firmware image that was issuing system calls. And there were way too many global variables. You have to be careful. Like PowerPC will do weird, I guess, like optimization stuff where it'll load a register like R29 with a value because it knows it's going to be accessed a lot. And you'll just see a random read from that value, and you have to go like 5 or 6 different functions up the chain to figure out what it was. So the decompiler looked at that, I guess, and translated it as sort of like a global variable, and then it sets it somewhere randomly in the decompile, and you got to go search for it. It ends up kind of being a pain. I actually spoke to their RetDec developers, and they gave me some advice on certain flags that you could set and some other analysis options that you could have used to sort of deal with that problem. We use Wireshark for the dissectors, so that we could extract programs and detect certain tri-station commands. We used uncompile6 for doing the actual Python decompilation, so we could read the Python. Post-analysis, I actually tested stuff with Binary Ninja. The MIL is actually pretty useful for evaluating the system call on certain functions. It actually handles it pretty well.
Yeah, and on the hardware side of things, I mean, it's pretty basic. I bought a nice stereo microscope a while ago, and that really helps, like soldering and desoldering TSOP chips. I'm getting older, and my eyes aren't as good as they used to be, so being able to hit the tiny pins is definitely helpful. I just use like a really cheap soldering station. You can get these things on Amazon for like $150. The flash reader is, again, it's like nothing that's super expensive. You can get it from mcumall.com. It's, I think, $100 for the flash reader, and I think those chip, they have a whole bunch of different chip adapters for different chip form factors. The TSOP 48 adapter is one of the more expensive ones, and it's like $40 or $50, I think. And of course, like a lot of X-Acto knives and flux paste and all the usual stuff you do for soldering. For PowerPC debugging, I've always liked this McGregor USB wiggler that I had, although it didn't work on this particular board setup. Some of that can be because, and you'll find this a lot in industrial systems, the processor will usually have some kind of external watchdog chip. Sometimes it's a small like SOIC 8 chip that has a whole bunch of different functions. Sometimes these engineers get a little bit crazy and they even design, watchdog chips that are used like with a little charge pump and a capacitor. But basically, its whole purpose is the processor has to touch the watchdog circuit, once every couple of seconds. And if it doesn't touch the watchdog circuit, then the watchdog circuit will toggle the reset line low, which will reset the CPU. That's probably what's going on here, why the USB wiggler didn't work. I did look at it with a logic analyzer, and sure enough, you'd see like a couple of bits go across the wire, and then reset would go low, and then the system would reboot. So I could probably figure out how that watchdog circuit works with time, but we were kind of in a crunch trying to figure out, we wanted to get the firmware out of the system, and we didn't feel like, tracing out a whole bunch of weird circuits on the board, so it was just easier to desolder. So if you want to become an ICS reverse engineer, like kind of on the hardware side of things, it's like being a regular hardware reverse engineer, I like to say, except that it's actually a lot easier to get into, because a lot of the CPUs and chips and things you'll see in industrial equipment is actually really old. Like the MPC 860, I think, is a processor from like the mid 90s or late 90s. It's one that's been around the block for a long time. All these like TSOP 48 flash memories are all pretty small, like 2 megabyte flash memories. There's not a whole lot there. It's actually a great way to get into embedded systems reverse engineering, and it stays relevant for a long time, because if you start REing some of this industrial equipment, it'll be in the plant for like 20, 30 years, right? Operators don't just replace this stuff every couple of years like you do with desktop PCs. So it's a great place to be. You just have to deal with conformal coding, and occasionally you have to deal with these watchdog circuits.
Oh, yeah, so if you couldn't tell by now, Reid's more of the hardware person, I'm more of a software person when it comes to malware analysis and reverse engineering. And so what I wanted to delineate were just some of the skills that you kind of need to deal with this situation. So in terms of our geography, Reid lives in a completely different state than I do in America, and if you notice, the hardware is actually in a different location. So I wasn't able to run any of the firmware code. I didn't try to set up QEMU or everything, I just did everything statically. So one of the main things here is you really kind of have to develop a lot of solid fundamentals. One, OS fundamentals, understand how system calls work, how they should operate just in a theoretical sense, understand what context switching is, how programs, processes load, those kinds of things. Sort of your standard RE things, but you'd be surprised how often you just sort of skip over. You need good static analysis skills. You just need to be able to read assembly code, right? You should be able to function without the debugger, and that was a huge thing in this particular situation, especially when we started out with the inject.bin and we didn't have the actual firmware to look at, just understanding the sort of calculations that were happening without running it. And then you really need to develop an adaptability to other assembly languages and programming languages. So the initial dump of software that I got before we knew anything about TRISIS, I received a .NET executable, an MFC, like Microsoft Foundation classes executable, and the Python code. And I had to analyze all three of them. And then later on, switch over to PowerPC and then analyze this operating system, right? So you really need to sort of develop the skill set, maybe study programming languages or something, to like sort of pick up these new languages on the fly. So you can deal with it. Other than that, just be comfortable reading specification documents. I think most of us in here are probably familiar with like the ARM spec and the Intel spec. But you have to go digging in Google for Freescale XPC 860 UM specification and read that as well. And then just, hopefully you can find a place that'll let you play around with this stuff. We've been talking to a lot of people here at Recon that have cool embedded jobs and things. Find a place that'll let you play around with this stuff and get comfortable.
Yeah, so I guess with that, we'll open it up for questions if anybody has any.
Booyah.
Hey guys, nice talk, thank you. So you mentioned you got binaries, but you haven't said where did you get them, and I haven't seen any hashes, if you can share that.
I think the hashes are public. If you
yeah,
look
we got the hashes from FireEye report and DHS report, and the samples ended up going on VirusTotal briefly for a little while, and we were able to get samples there.
I think the initial dump of software we got through one of our other sources, but I don't remember honestly where that is.
So the documentation itself also just Googling, or were you able to get
That's-
some of that from the manufacturers?
Yeah, so the documentation's kind of interesting. So if you actually go and search for Triconex, the Triconex documentation, like the programmer manual and all that stuff, most of what you'll find, and if you go and do this right now, most of what you'll find is actually on the U.S. Nuclear Regulatory Commission website. And it's kind of an interesting aside that the Triconex safety system is classified as able to be used for safe shutdown of a nuclear pressure vessel, which basically means it's like, you know, a thing that's designed to look at a nuclear power reactor, say things are unsafe, and shut it down. Of course, there will be, like we said, a lot of mechanical fail-safes. Engineers don't trust these newfangled computer things. That won't be the only thing that can scram a reactor, you know, shut down the reactor, but that will be one thing that can.
Hey, do you think that the that the victim was just running the the module in program mode, or how do you think the attackers got around that?
Say that. Sorry, could you say that one more time?
Sorry. Do you think that the victims were running the module in program mode, and that's how the attackers got around the requirement that be in program mode?
I mean, it had to be. The installer, the trilog.exe loading the inject imain payload, it will not install unless the thing is in program mode. So the installer portion, it would have had to been. So we don't know if maybe the safety systems were like in a maintenance cycle or something. Maybe they were testing them for some reason, but that's the only way it would get on there. Once it's on, the actual rootkit network command stays resident regardless of the key switch location.
Yeah. Did you notify Schneider about this at all, or file a CVE? And if you did, what was their response?
Well, so there are actually CVEs for the vulnerability that was used by TRISIS. DHS or NKIC or whatever the organization is called now, the U.S. Department of Homeland Security, published advisories about the memory corruption exploit, right? The privilege escalation by overwriting 2 bytes. They didn't publish a lot of technical details on it, but they at least said, yes, this vulnerability exists. They gave it a CVE. The initial version of that advisory advised end users to upgrade to Triconex version 11 in order to mitigate the issue, which actually requires replacing your processor modules. They since took away that advice, and last I've heard, Schneider is working on a permanent fix, you know, firmware fix for the version 10 systems, which are affected by this. But yeah, there are CVEs.
Yeah, we didn't talk a whole lot about the sort of timeline for this attack, but Schneider was notified almost immediately in this process. Like, what was it, back in October, November? Right. And Schneider, as a ICS vendor, has actually been pretty cool about this. Like, they opened up about it at like S4 and talked about what happened and some of the basics of the attack and everything else. So we've been in open communication with them for a minute now.
Okay.
There's one more question.
What other security systems did they have involved, like to protect the network? 3 years ago, I was at SANS talking with people about ICS, and the biggest problem was that these systems weren't designed to go on the internet, and people just were hooking them up willy-nilly. So do you know from the customer what other things were in place that were circumvented as well?
Yeah, we really don't. So we don't have any information about the victim, it turns out. So yeah, I believe FireEye did the incident response for the victim, or at least they were on site at one point during the incident response. I think they have a better idea of like what the actual network layout was. I will say that there are, there are a couple of different safety groups that have advised architectures for safety systems where they would usually say, you should have the safety system connected via a serial connector to like the rest of your distributed control network, your big control network, and you should really only be able to read data over that serial connection, right? So there should be no commands that even allow like write operations. It's probably safe to say that the victim, had the safety controller like probably on the network with the rest of their, their control system, and probably not very well segmented based on what we understand, but we don't know for sure.
Yeah, I mean, it would have to clearly have been a misconfiguration issue. There's no other way around it. When we're talking about about this, like one of the things we remind a lot of our customers and defenders in general is like Trilog didn't just magically show up on the engineering workstation. There were a lot of steps that led to it IT network, whatever, pivoting into the OT network, and then finding their way to the engineering workstation, and then finally loading the payload. There were a lot of things that sort of the defenders at this site missed before the actual TRISIS event happened.
Was trilog.exe, is that a normal executable that then the attackers added this Python code into, so it would be expected that trilog.exe was run and they just like implanted their malicious code into it, or was it a whole new executable that they created that didn't previously exist?
It was well, the name existed. So trilog.exe was actually, I actually looked at that, the original trilog.exe is if I remember correctly, it was a .NET program for querying state on the controller. Like, let me just, the firmware has like this event logger thing, and it writes like these messages, and then the trilog.exe basically queries these messages from the controller and spits them out to the engineer. So that's just sort of monitoring the safety system state. So what the attackers did, where they made a separate binary, pi to exe, and just named it trilog.exe, I guess just in case one of the engineers saw it, right? They would be like, oh, well, that's just normal, that should be there. Interestingly, though, I don't think the trilog.exe Python executable had the right icon. So if you're actually looking at it on the Windows desktop, it would have just looked like, the generic like little box with the green window. Whereas if you have real trilog.exe, there's an icon that has, I don't know, some weird 8-bit looking logo on it.
Hi, thanks for the talk. So the question is, can you guess how this 29 command would be issued? Like if it would be operational?
Sorry, can you repeat that?
You have a 29 command that was installed. So who would be issuing it command to make it operational?
That would be the attacker would execute that command as kind of a post-exploitation step. So we did write some tools to actually use the network command 29 and actually exercise it. But it would be the attacker in this case would be first they would load the rootkit into the system, then later they could use that network command 29 to do stuff. Other than that though, other than by an attacker, it would never be used.
Okay.
Yeah, the interesting part about that was that, there's sort of some evidence here that they were probably testing this capability, and Reid and I were talking about this part yesterday, that if you actually look at all the code, they never use the rootkit, they never test it, so they have all this debug information for installing the rootkit, making sure it went well, everything else, and then they never launched anything else. They never did anything even to test that the rootkit was installed and would give them a response back. I don't mean the next step in the attack in terms of making the controller ignore safety values or anything, but it's possible they were still developing this capability and they were just testing the rootkit installation, and then later on they would have tested how the rootkit goes back and forth. It's possible that they picked an empty network command so it wouldn't accidentally get triggered by regular TriStation software, because that would be weird. You send the wrong value, then you will definitely crash the controller if you accidentally send a write or an execute to a function address that has no code, right? So. Yeah, so what we think is, so his question was whether or not there was another component involved here. Yeah, so there would have had to be, there are two other things if you wanted to make TRISIS a legit attack besides just sort of giving you access. You need to send a PowerPC payload to the rootkit that would cause it to bypass or basically ignore certain inputs, right? It wouldn't read certain values, or like you saw in the slideshow, modify outputs so that it would always look safe. So when the controller looks at what's going on, it'll say, oh yeah, this is fine, right? You're basically just kind of putting a blindfold on the controller. The next step would have then, there would have to be another payload somewhere else on the OT network to actually cause an unsafe condition to happen, right? So you still need both of those things, and that would be completely unrelated attack. That doesn't have to be a Triconex thing. It's probably another control system attack or something.
Right. Some regular control system manipulation.
Yeah, they didn't quite get there, but they got pretty darn close in terms of causing something to happen.
Okay.
So if there are no further questions, thank the speakers again.
Booyah.